Welcome to Calculus. We're going to do a couple examples in the book from 2.6. A lot of you are having trouble with this, so I've really tried to look at most good problems I can come across. Those are the ones I've assigned. But the examples are kind of untapped. I've referenced them to you, but we haven't done any. So I'm going to do these, just kind of talk through them. I'm going to start with example 3. I think I'm going to do 3 and 4. I might, probably not in the same video, but we'll start with 3. So it says air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. So I'm going to write that out, 4.5 cubic feet per minute. One thought is it says per minute. This is a rate. It also says it's pumped in at a rate of 4.5. That's a clue. This is something d something over dt. What is it? And you might notice it's feet cubed, so that's volume. Doesn't use the word volume, but we know that that's what they mean because cubic feet is volume. It says find the rate, so they're going to tell us in a second what this is going to be, of change of the radius, and then look for that word when. There it is. When r is 2 feet. Okay, so that means I want an equation for a sphere. This is a spherical balloon, it says. So the equation for the volume of a sphere, this is not one I would make you know. The volume, though, of a sphere, because that's the equation that would relate V and R, is 4/3 pi r cubed. If I were to take the derivative right now, I'd have a dV over dt. I want that. That's where, we can plug that in. I'd have a dr over dt. And that's totally fine too, because that's what I'm looking for. So actually that's necessary. So it becomes 4/3 times 3 pi r squared times dr over dt. That's going to be, those cancel. And so when we plug in, let's do it over here. We'd have 4.5 equals 4 pi. Now that we've taken the derivative, we can plug in for r. Don't forget the square. I don't like this decimal, so I'm going to change 4 or 5 to 9 halves. I'm going to multiply it by 1/4. 1 over 4 pi, I guess. And then another 1 over 4 for this 2 squared equals dr over dt. So what do we end up with? We end up with 9 over 32 pi. That's what the book says. 9 over 32 pi, and this is feet per minute. That's our dr over dt. That's it. That would be, I would rank this one as a, I'd say 1. The equation would be given. There's no substitutions to be made. There's only 2 variables. Pretty nice. Yeah, we had to square a number. We had to deal with a pi, but doable. Okay, I'm going to just keep going and do example 4 now. Hopefully that helps. On to example 4. Okay, example 4. This is on page 152. And you might notice I did not rehearse this, so I might mess up. I did read through it a little bit before, but this is example 4. I did read through this a little bit. Okay, this one is about an airplane flying overhead. We've done a few of these. I think all the ones we've done, though, have had to do with angles. And so we've had to do a sine or a tangent or something like that. This one, they never mention an angle. Well, let's read it. An airplane is flying on a flight path that will take it directly over a radar tracking station. As shown in the figure, if S, you can see that in the figure what S is decreasing at a rate of 400 miles per hour. When S is 10 miles, what is the speed of the plane? No mention of angle. We don't want an angle. We don't have an angle. So let's not do anything with an angle. And they drew a nice picture, which I might not always give you a picture. They even tell you it's a right angle. They tell you this is S. They tell you this is 6, and I can put that as 6 because that's not changing. The plane is flying along this path, so its altitude is staying 6. They're going to call this x. And hopefully the equation is kind of screaming at you in the face. Pythagorean theorem, right? Pythagorean theorem. I could write that in big red letters, but I'd have to erase it, so I'm not. I'm going to just imagine flashing red, green, yellow letters, Pythagorean theorem. That's what we want to do here. Be thinking of, if you hear an angle, it's going to be a trig function. Otherwise, it could be your volume, your surface area, your area equations, Pythagorean theorem. That's pretty much it. We've done it. I think we did the. We've done some proportions, similar triangles. Those are some tougher ones, but look through the examples you see in the homework. Lots of Pythagorean theorem. So I'm suspecting we'll do that. Let's read this a little more carefully. It says S is decreasing at a rate. Right away, it's saying the rate of S with respect to time is decreasing, so I'm guessing it's going to be negative, of 400 miles per hour. Ooh, they didn't tell us it was negative. We had to know decreasing meant negative. I'm going to write this old school, I don't know old school, but I'm not going to write MPH just so we can see that this is a rate for sure. And notice the way the question is phrased. It says, when S is 10, what is the speed of the plane? That's the same thing as saying, what is the speed of the plane when S is 10? Since this plane is flying along this path, right, it's flying horizontally, parallel to the ground, we know that our dx over dt, or what they're asking for is dx over dt. The plane is not flying along the hypotenuse. It's certainly not flying vertically along that line with the 6 mile label. It's flying parallel to the ground. So dx over dt is appropriate to use there. You know, this triangle could have been drawn this way. Maybe you like it better. Where here's the ground. This is still 6 miles. This is still S. That would be S. That would be fine too. I'm not going to do that because they didn't. But if there was not a drawing picture given, you might have thought to do that. It's the same thing. But in this case, maybe it's a little easier to see the plane flying along that X. I need space. I'm going to erase this. My big eraser. Okay. Alright. So dx over dt is what we're looking for, and there's that magical word when. We always look for that. When S equals 10. Okay, so I need an equation. I want to find dx over dt. I know I'll have to use ds over dt, so I need an equation that relates S and x. Well, like I said, Pythagorean theorem is going to be the way to go. Make sure you get this right. The S is the hypotenuse, so it's x squared plus 6 squared equals S squared. If I were to take the derivative right now, it would generate a dx over dt, which is great because I want dx over dt. It also generate a ds over dt, which is great because I know ds over dt and I want to use it. Whoops. Forgot this, didn't I? 2s ds over dt. Cancel, cancel. Now this is 6 squared. Nothing. It goes away. You might think, oh, it doesn't matter, but it does. Actually, you're going to see 6 does play into this solution in a moment. So you think, easy problem. This is an average one because there's going to be one little challenge coming up. And here it is. What's x? What is x? Well, we don't know. So we're going to do this later. But have a little aside here to do a side calculation. At this instant, I've taken the derivative, so I can use s is 10. When s is 10, what is x? It's 8. That's a Pythagorean triple. Know your triples. Makes life easy. So we do know that at this instant, x is also 8. So we can plug that in. We don't know this. S, we were told, is 10. This is negative 400. If you miss the negative, it wouldn't be that big of a deal. You would end up with, because we're going to have a negative dx over dt right now. Now it does say speed. If you've had or are taking physics currently, you know that speed is always an absolute value. So it wouldn't have mattered really. But it's good to be consistent. So if we divide both sides by 8, you're going to get dx over dt is negative 500, and the units are the same as ds over dt, miles per hour. Now since they asked for speed, I guess we'll just give an absolute value and of 500 miles per hour. That's it. So I kind of went through those fast, but I would look at the other examples as well. 2 is a nice, easy one to look at, relatively easy. 5 and 6 are pretty good ones. 6 is tough, using law of cosines. But 5 would be a good one, but these 2 I think are probably the best ones. So I hope it helped. Again, read the question carefully. Find out what your rates are. If you see it is per hour, per mile, per hour, per minute, per second, that's a rate. It's a d something over dt. There's going to be the word when, probably, near where it's telling you what you're looking for. Those constants you can't plug in until after the derivative is taken. Certain times there'll be things that don't change, like in this problem, the 6. The 6 doesn't change, so you can plug it in the beginning. But of course, x is changing, so you don't want to put 8 in for x until after the derivative, until you are able to identify that instant when the derivative, when the rate of change is whatever you're looking for. So that's the basic idea. Make a sketch. Think of equations. The toughest part probably is this stuff a lot of time when it's a letter substitution. I think I was working with someone today, number 111 on the review. Those are tough. You're just going to have to try some things, test it as the best you can, and I think you should have a good amount of time for the test. So hang in there. It's going to be good. I'll be at school at 7:15 tomorrow. See you then. Bye.
Made with Doodlecast Pro.